Welcome everybody. I'm Benoit Moncon, professor here in SYE and director of the Supply Chain Logistics Institute, as well as the Physical Internet Center. I'm very pleased to have you around. We have the honor today of receiving Professor Eric Ballot. I've been interacting with Eric since over 10 years now, okay, basically, and mostly around the physical internet. Professor Ballot is a professor at MIN Paris PSL, so Paris Sciences and Lettres. Don't try to understand too much all those acronyms, they're changing every year. Essentially, this is top engineering school in France, and he's leading their lab on scientific management. And he's heading also they have a chair on physical internet over there, which has multiple companies involved in the chair, and he's the head of that chair. Eric was among the three first academic person, and in fact I should say persons, to work on the physical internet with me. And so that was at the beginning, and since then he's been active in many projects, research, but also interacting with industry and governments all around. Sorry, I'll stop talking and give him the floor. So welcome, Professor Ballot.
Thank you very much. Thank you, Benoit, for this very kind introduction. It's a pleasure for me to be with you today. Can you hear me? Is that okay? Yeah, is that loud enough? Okay, so I'm going to talk about one of the subjects we try to tackle with the concept of the physical internet is routing. So how we could route containers from one side to a network to the other side of the network in the right manner. So that's going to be the subject for today. I have, I think, 45 minutes, and then we have time to discuss all points you would like. So routing is a very well-known problem. I will not go into the details, but there are some specific points when it comes to the physical internet, and I have a couple of examples of what we did and obstacles we still have. So from my point of view, it's not really working yet. So more research is needed. And I'm going to share with you research that is really now underway to overcome some limits that I will present just before. So routing, finding the best path. In logistics, most of the work is dedicated to vehicle routing. Here, I'm not going to talk about vehicle routing. I'm going to talk about how we could route packets or boxes or containers, which is quite different. And we have different types of routing, unicast, one-to-one, broadcast. Of course, not all types of routing are suitable for logistics. Maybe so far we don't do any cast. Some send something to anyone. No, we are much more specific. Geocast could be interesting for us. But here, to be interested in routing, we need to have at least more than one route. And in many supply chains nowadays, we just have one route. We have one transportation scheme to reach one customer. So routing is not a problem at all because we don't have routes to go to different customers. Another point is routing allows dynamic choices, which is something we don't have a lot when you have your own supply chain. Another point I want to highlight to start with, usually when you think about the physical internet, you say, oh, it's going to be a nightmare because we're going to go from one hub to another, and it's going to cost arm and legs in transshipment cost. But when you study networks, all kinds of networks, transportation networks, ecosystems, maybe Facebook, in 5 jumps, you know everyone. Brain, in 5 connections, done. And I guess it's going to be the same thing when a network is properly organized. In 5 jumps, you on the other side. maybe 90% or 95% of the time. And of course, the routing depends of the network configuration. If it is a wired network, if it's a hierarchical organization, or if it is an ad hoc organization, or in logistics we call it on demand. So there is nothing already in place. And we could have end-to-end or not, like the digital internet. It's not really end-to-end, but for logistics, I think that end-to-end is something that we should look at, because, of course, we need to have proof that we're going to reach the end. Could be static or dynamic. Oh, sorry, there are two French words here. Sorry, it's not my mistake. It could be done by one agent, or it could be decentralized. One agent is, we know that for sure, and we have a lot of good and old algorithm to find the best routes with advantages and disadvantages I won't discuss. The literature on the subject is really, really huge. But here, maybe we need to route with multi-agents. And here it's quite hard, because the proof of optimality is much harder to have. And we are not starting from nowhere. We have more than 70 years of intense research and development on the subject. I want to put routing in the context of interconnection, because physical internet is interconnection of logistics services. It's just a small part of the global picture of the interconnection. So don't misinterpret what I'm going to say about routing or application you could have in your mind. With routing, we're just moving things from A to B, right? And it's also, we have a more a simplified interconnection system with the internet with less layer. But what is interesting for us, and it's a work that we did, yes, more than 6 years ago now. It was published 6 years ago, but on interconnection model. Here you may think about how to manage your inventory or to deploy your product over a territory. But here, I'm going to talk today mostly about two layers, which is the routing layer and the network layer. And I will left the other layers on the side. So routing layers provide functional and procedural means for getting a set of PI containers from its source to its destination. So the definition that was given at that time was unicast. One source, one destination, in an efficient manner, and with different nodes involved. When we go to the network layer, it's a bit more operational. Here we are mostly at the level of all nodes and arcs, and we have to manage the loading, we have to manage the capacity of each asset involved in the process of moving things. So the routing, we do the global route from A to B, network layer. What we do is how we combine the resources to make it happen in the best way. So among the 7 layers, I'm going to focus on 2 layers, routing and network. So here we mostly work on simulation with unicast, and also I think we should work, but I haven't seen a lot of work on this, what I call groupcast. Because if you are a customer, if you order online, maybe you order not just from a single company. You order from many companies. And then you have been delivered by many carriers. But maybe you're going to be interested to receive everything at once. Or as a factory, if you're a car manufacturer, you're interested to gather all the parts all together, not in different shipments. So something that maybe we should take into account in the near future. So here we try to combine resources to ensure container end-to-end routing. That's my main goal. So it's quite different from vehicle routing. So we need to know all accessible services, which is not a given today, because we need some kind of universal language to publish all the offers. So I could search offers and combine them. It's also, there is also a need of dynamic adjustment because it's pretty sure. And I'm not talking about French strikes that we have nowadays in France, but it's pretty sure we're going to have disruptions, we're going to have trucks, we're going to have arrive late, we're going to have a train delay or whatever. So we need to readjust the route continuously, otherwise it won't work. And of course, we have to decide what is the best route. It is the shortest, it is the with the less environmental footprint, it is the fastest, should be decided. And also, I want to point out that it is a big difference with the internet. In the internet, you have a very limited infrastructures, because every time you need to build a new fiber network or whatever, it comes with a huge cost. Here, we are interconnecting logistics services. And logistics services, you can create services for almost zero cost. You say, oh, you need a truck at that place, I'm going to send it one to you. The cost is almost zero to start this new service. So we have already a lot of regular services, but we can also create a lot of on-demand services, which means that the topology of the network is completely different from the internet network, where it's mostly based on the infrastructure. And one of the challenges that we have is how we could reinforce the best routes, because we create routes every day, every minute. We create new services. And the main challenge, and with Benoit, we are very not interested, it's not the word, but we really want to help to solve the environmental challenge ahead of us. So we need to build new efficiency. And it's really hard to build new efficiency when you have so many offers, which is the opposite of a natural concentration that you have with the digital internet or you have with ports or airports, because you cannot duplicate the infrastructure. So, OK, here is my problem. I have a set of my typical supply chain. I want to publish from every node of the network or all the services that are available, not only for transportation, but also for inventory management, storage, picking, or whatever. But here, I'm going to focus only on transportation. I could have different offers, routing number 1, routing number 2, different characteristics. And I'm going to, then with my routing algorithm, I need to choose what is the best one. That's my main problem. So when it comes to that problem, here, we deal with not just one company. We are not under one roof, so we are not dealing with cost. We deal with tariffs. And if I look at typical, here it's in orange, typical cost, forget about the kilometers, just, or the distance, just take, here it's pallet, but it could be unit load. The tariff that we have nowadays is something like, you know, if you are able to fill the truck or fill the train, I'm going to give you a better tariff. So you have some kind of incentive to fill the transportation mean by yourself. And it's consistent with mass production and mass distribution, because you have enough volume to fill a truck or even for some players, a train. But the main problem that we have now is it's over. You cannot fill transportation mean by yourself, less and less. Because we started with, trains full of iron. And now we are heading to book delivery or kilograms. So it's not part of official statistics, but I think it should be very interesting to have official statistics about this subject. I found a survey in France. Maybe you have other surveys in the US. The medium weight of a shipment was 160 kilograms in 1988. And in 2004, it was 30 kilograms divided by 4.5. It's huge. Huge change. If I continue the trend, and I'm pretty sure that that trend is still there, because in 2004, Amazon, Alibaba, and the others were almost zero. Okay, so it's maybe 6 kilograms in 2020. And if it continues that way, it's going to be 1 kilogram. Sorry, it's metric. But maybe 3 pounds, something like that, 3 pounds in 2030. So, okay, we're going to have drones. I see just one problem. With drone, of course, routing is done because you should ship directly. So, problem solved. The only issue is here, if you take the payload, and here you have the emissions as a logarithmic scale, the drone is somewhere here close to the van. So, because of course, if you deliver things one by one, you need a crowd, a massive crowd of drones. So it won't be the solution. The solution is still the ugly truck that appears here as a very nice transportation mean. And of course, you could add here the train that is even better. So the biggest, the better. So to make it happen, you need a new level of consolidation, of flow consolidation, and it's part of the routing to make it happen. Should be part of routing algorithm to make it happen. So let's come back to the cost. Of course, you know that in transportation, if we have no economies of scale, like in a drone, when you need to ship 2 parcels, you need 2 drones. No economies of scales. You ship just directly. When you have some economies of scale, then you use a transshipment point to consolidate the flows. Okay? And when I look at my trucks, the cost is almost flat. Because the variation of the consumption between an empty truck and a full truck is something like 30% of gas consumption, additional gas consumption. And the gas consumption is maybe 1/3 or less of the total cost of transportation. So marginal variation. So we should have a high level of concentration of flows everywhere, but we don't have that. One way is say, okay, but there are other systems like marketplace, freight marketplace, and they could play with marginal costs. Like, you know, you go there, you come back, why you don't just pick something on your way? It's not really on your way, so it comes with a marginal cost that is not zero, because you should divert from your original route to pick something else. Okay? It brings extra revenue as well, but it still comes with a cost. So we want to encourage more and more loads per trip. So for that, we did a simulation a couple of years ago where we had a network. So we optimized with EPFL, which is an engineering university in Switzerland. We optimized a network that we call our physical internet network over France for fast-moving consumer goods. We had lines operated regularly between major hubs, and they were selected by the routing algorithm according to their cost. Okay? And we had also on-demand services, also selected according to their cost. Because in the big simulation, it was like everything was cost-based. So we optimized everything, so the routing algorithm worked on the cost. It's like there is just one company. Of course, it won't be the case, but for the simulation, it was just like one company. So same rule for everyone and no competition between the players. And the shippers here were well represented because all the requests from the different shippers were not coordinated. So shippers requests well represented. Transportation markets not so well represented, okay, in the simulation model. And we did that with multi-agent model, and we implemented routing layer and network layer. So what we did that model, and where we combine containers and we route containers. So we had a couple of problems to solve. The first one is fill containers with orders. The second one is find the best route. And the third one is optimize our operation in each node. Okay? So the first one, it's not really the main topic here. So it's something like bin packing. You know, you have a set of all products, and you want to combine them together in order to fill the box, and you have a choice of boxes, and you pick the best combination of boxes according to your preferences. Maybe just one big box, but that maybe at some point you need to open it and break it, or small boxes, and you do the trade-off, okay? But the second point is the routing itself. So here, in the simulation, it's really easy because you know all services. Problem solved. You know all services, and you just have to pick, and you have a number of algorithms. So here we use state link routing algorithms. So we have a map of all the services, and we compute the route within the map of all services. So to do that, we use an algorithm which is A star. Maybe you know it, quite efficient. Maybe not the best one, but for a simulation it's enough. And we tested with different criteria, and even we could combine them. Not too fast, not too expensive, that kind of thing. But when we arrive in a hub, we have no synchronization of inbound flows, but we have visibility of incoming flows, which is something we don't have in the trucking industry. I don't know in the US, but I'm not sure that in all warehouses they know exactly when all trucks will arrive. They have some kind of ETA, estimated time of arrival, like for the aircraft. In Europe, it's not the case. So it should arrive, and then, hey, here I am. So they lose time at the gate and everything like that. So here, almost the same thing, but for the routing, we have more visibility. It's not like the internet. You know that you're going to receive a packet before you have the packet. So you have an advantage. You can know the state of the network, and you can anticipate loading here, and and make good trade-off between waiting and fill rate, because you know exactly what's going to arrive. So you don't have to wait until the last minute to leave, just in case there is another container that will arrive. You know that no more containers for this departure, so you can leave as earlier as you can. You can leave early, and then you keep some margin for the next hub. Well, so basically, this is the main algorithm. Of course, it was implemented, and it seems easy, but it was a PhD thesis and quite a large project, and it took 3 years to put all things together, because here you need to do bin packing problem with multiple bins and time window. So here already you have an optimization algorithm that is not that simple. Routing is another optimization algorithm that is not simple. And to make the simulation work, you could have millions of runs of optimization in one simulation run. Okay? That's what was done. And of course, you could synthesize everything in a single slide where you have everything. Container loading done, find path to destination, no, find another path, find departure, yes, next first step, arrival, yes, unload container, no, go to the next step. Very easy. So that's the flows that we took into our physical internet network. So we ran the simulation, and we had great numbers. Great, but we have an issue here, because physical internet works when it exists, but it doesn't exist. So we have a chicken and egg problem to solve. So if it's there, it's nice, but how to make it happen? How to start with that problem and gradually shape it so we arrive to the right hand. Okay? That's the main problem that we have, because you can do routing here, but it's not the main point. You should start with here. So what kind of evidence do we have? I found an example of routing in a network. It's a French startup, but maybe you have the same kind of startup here. This one is Mr. Pasha. Mr. Pasha, you know what it means, Mr. Pasha? Pasha means a lazy guy, you know, always in the couch, watching TV, things like that. Not pointing at anyone. Mr. Pasha, so what they provide a service for all the shopping that you do online. They deliver everything in one shot. So you don't have anymore all the carriers, one after another, looking for you. You're a Mr. Pasha customer, and you pick the service you want. Delivered everything on Saturday afternoon, because I'm going to be back on Saturday afternoon, or deliver every night between 10 and 11, because I'm a consultant and I want to have my things as soon as I want them, as soon as possible. So how they interconnect things, how they do the routing. They cannot change all the interfaces of all players. You know, they cannot, as a startup, knock to Amazon door and say, you should change your website so you have Mr. Pasha inside. No, no way. So what they do, when you enter your address, I put my name, and instead of my own address, I put Mr. Pasha Distribution Center address. And that's it. Interconnection is done, the address. So all my deliveries, they go to Mr. Pasha. And then Mr. Pasha gather my parcels, and then they organize the delivery to my place, because they know me. I am Mr. Pasha customer. I'm never DHL, UPS, FedEx, and the other customer. So they don't know me. You see the difference? And the problem is, you can imagine that for FedEx and the other, it's nice, because instead of delivering hundreds of points, they deliver everything to one point. But they won't pay for that. So Mr. Pasha asked me some money to deliver something once that is usually delivered in several times, which is, when you think about it, a little bit crazy. It's a bit absurd, right? Because it's more efficient, but as it is, we have to pay for that. So of course, they build new services, they enhance the experience and things like that, but it's tough. So here, again, we still have misaligned incentives. So the cost function of the tariffs are not in favor of concentration of flows and routing. And I found in Italy a system to, you think it's normal to be delivered by different companies the same day. We're used to that. So in Italy, they play the game in the other way. They say, we should increase the competition between the postal services. One operator is not enough. We can have several operators. So what it means that you can have the red box for the traditional operator, and you can now have the yellow box for the new operator, and they may have also another operator with another color. Just to make things easier, the logo of this company is yellow, but the box are red. And of course, you need different stamps, because there are different companies. And all the tourists, they miss the stamps, they are confused, they put the postcard with the wrong stamp in the wrong box, and it's a disaster. And you can imagine the efficiency of when you need to collect all postcards, of course, with different vehicles, because they are competitors. So we need to find ways to better concentrate and offer alternatives. So in France, a startup started, CRC, and they are pretty good now at concentrating flows. But so far, they concentrate for themselves. So it's more like an intranet routing. And so far, it just goes one way. So they have a small network with 6 or 7 ring centers, but they just manage the flow one way. So it's really simple routing algorithm, no big deal so far. And one way, always one way to reach the end customer. But now we have a project where we're going to use them in a reverse way. Traditionally, we use them to ship goods from the north to shops to the south. But now we're going to collect goods from the south and also ship them to stores to the north. So it's going to be more a network, or at least a physical intranet. And we are now building some algorithm to concentrate the flows on each router. So to bring an incentive to all companies to join that system. And the good news is we have now a competitor of CRC that could play the same game with the same prerequisites like EPC Global, SSCC codes, and things like that. So they could be compatible, but competitors. Then it should be the first internet, because so far it's still an intranet. So far we don't have clue of or evidences of routing, I mean in inland transportation. So I tried to summarize a couple of questions, and now we enter the most recent work, how to avoid the malediction of always too large truck or not full trucks. Okay? Is it inevitable that competition ruins all efforts to consolidate flows? Are we going to suffer from that always or not? And how we could design new and more virtuous mechanism, and how this mechanism could be accepted by the players. Are they going to be interested, or they say, no way? I'm going to play with my trucks, and you don't have one, stay away. Okay? So for that, we use mechanism design theory. I don't know if you're familiar with mechanism design theory. It's part of game theory, but with many, many players. Because game theory, usually it's 2, 3, 4, 5, maybe 10 players, but no more than that. And we do some experimental economics with the game. So here in Europe, we have a good playground because we have now a network. So we have something to focus on. We have at least the skeleton of corridors where we could concentrate the flows. But we still have the problem how we're going to concentrate, how we're going to give the incentive to the players to use that network. So we are working on different techniques for transshipment in a European project. We want also to allow request reallocation when you have a container. If there is another player in a better position than you, there is a mechanism so you can exchange the load with him, and you have some extra money because it's better than you. And he will make some money as well. So there is an incentive for both. That's what we call request reallocation. We want to favor multimodal transport, and it's of course it should work with many-to-many open network like spot market, also with up and fixed lines. So here is a very simple skeleton of that problem. We have a set of hubs, and here is a tree, but it works also with a network, with a mesh design. You have a couple of requests, and here we have transportation requests 3 and 4, so that are together already, and 6, 7 that are not waiting for a carrier, and 5, 1, and 2 also waiting for carriers. As it is today, this player says, you know, I have 3 and 4, I'm going to do my job. And that's it. But what if we propose to stop at 0 and maybe reconsider what he does? So to make it happen, we need to set up a mechanism where we don't have to disclose all the information A carrier will never tell you the fill rate, the actual fill rate of its truck, like an airline. You have a price signal, but you never know how many seats are still available. That is really a confidential information. So we need some proxy agent to organize what is a combinatorial auction. And this combinatorial auction allows the information to the request to be transferred to the carriers. So the carriers could do all kind of computation about all the bundles they could propose and the price they could submit for the bundles, different requests together on each route, as many as they want. And then they do the proposition, it's validated, then the auctioneer compute what is the best solution, and then the requests are allocated to the different players. Okay? So here it's an auction mechanism. It's quite different from the auction mechanism used in the industry nowadays. In the industry, you have mostly reversed auction or Dutch clock auction, like with the price is going down, owned by the shippers. Here it's a combinatorial auction, not owned by the shippers or the carriers. It makes a huge difference. The people who owns the auctions could play with the system. And here, the best solution, according to the price submitted by the different players, is that maybe carrier number 1 should drop request number 3 to another carrier, and we'll have a full truckload with 3 requests to hub number 5. So here is an example of recombination, reallocation of flows that help to. So here we could change the route of the vehicle routing, and we could even change the routing of the containers, and we do both together to optimize the whole solution. Okay, and it's based on the price submitted by the different players. That's an example of what we could do. But if I have to enter with the professional all the details of the optimization and things like that, not interested. So what we want to do now, and it's part of a new PhD student job that I have, is to better understand how the player deal with price proposal and how it may shape consolidation or not in a very simple market. So we want to understand the difficulty of transport companies to increase their gain, find mechanism for more reliable and efficient transport markets, and understand the behaviors of the actors when they play among each other, what kind of strategy they may use. And is the strategy a virtuous one, or is it harmful for everyone at the end of the day? So for that, this is the prototype number 1. Now we have, so this is a truck. This is a truck, believe me. This is a transportation request. This one is already on the truck. This one in the corner means already in the hand of someone else that's going to pick it, things like that. So we have here 4 trucks, 4 players. At each round, we have new transportation requests. And as all companies nowadays, you chase for orders. So you submit price and things like that. And even a small country, with 9 regions, it's already tough because you have a lot of combinations. If you combine the different requests, the routes, and things like that, the solution demand is already huge. So in the back office, we have MATLAB, and here we have a very simple. Here is a game we play with some professionals. So you take your phone, we give you a link, and with the link you could submit where you want to go, what do you want to pick. You could then propose a price or propose a cost structure plus a margin. So we can experiment with different cost structures. And then when you're done, you push the button, and then when all players are done with the round, we have the results, who got what, and then they do the routing on the board. Okay? And of course, we use that. So we play with different players, and we know that the game works well because at the end of the party, The average fill rate of a truck is around 50%, so it's not that far from what we know. We also know that when we have well-trained professionals, they have better results than the others. So it's not a random game. It could be something that we should check, because otherwise it means that you can do whatever you want. At the end, it's just luck or bad luck. And in the back, we can compute the optimal solution. We can check the gap between the optimal solution and the solutions built by the players. And we try to identify what are the main parameters, the main drivers of that gap. And for that, we could change the different incentives. We can change the layout by putting a hub in the middle, so to concentrate the flows. And at each time, we change also the cost structure and things like that to feel what is really influential on the result, and how we could align the behavior, the incentives, to end up with a much more efficient transportation network. So we use that game. So far, so you need MATLAB, and you need a table and a couple of things to make it work, with some links. So we start to play that game with different people. If you're interested, I can share it with Benoit, so you can also contribute and bring more results, so you have a more solid database to do the analysis. So it's also quite inspired by the beer game. You know, in the beer game, originally, if you read the John Stearman article, it was to understand how when you take an inventory management decision, what do you have in your mind? Do you have the delay in your mind? Do you have the lead time in your mind? Do you have that kind of things? And the beer game helped to prove that you forgot about what the backlog that you have and things like that. Here we want to do the same thing. That's our goal. We want to understand what is the decision process behind. I'm going to go there, and I'm going to pick that order. Is it really the best decision you can take, or is it the decision that you are just able to take because of some cognitive bias that you have, or some cost structure that you have in mind that are maybe not relevant anymore? Okay? Like, I need to fill my truck. So I'm going to run from one side to the other, like here, from one side to the other of the board just to fill the truck. Is it the best solution? Maybe not. Okay? And we're going to play that at Epic. And when we have good cost structure and good incentives, we're going to implement that in the CRC operational system. So we're going to see if it works or not. But before we play with the company, we play on the board. And then when we have something that is relevant, we're going to implement for the different operations. So I didn't went through the details here, but we are still far from a solution to that problem, because we are not able to describe everything in the same manner. Even locations. It's a nightmare. It's a nightmare. I heard that in Europe, up to 20% of addresses are not fully accurate. And all the carriers, they try to maintain databases of addresses. It's a nightmare. Of course, you may think that maybe Google is going to solve that for everyone, but maybe it's not what we want. So we are working on a collaborative process to maintain addresses accurate for a community of logistics service providers, so that they don't have to maintain. But also we need, to also communicate information for the bidding process. If everybody communicates in a different way, it will be impossible to do the routing with multiple players or multiple stages. We are looking at different technologies, maybe standards, okay, nice, but a bit old-fashioned. Simple links, I'm not able to develop that point, but if you can check simple link, consumer goods forum. It's interesting. Blockchain, but also we invest a lot in API. How we let flow automated programming interfaces. How we let flow the information from one system to another. And of course, we have many theoretical problems to solve. For the best ruling, the complexity, what we do with 10 players, how we could scale it to thousands of players. Will it still work or not? Or maybe we should downgrade to something that would work and would be scalable. And once again, incentives. With that, I thank you very much. I do apologize for the French accent, except maybe for the French audience. But thank you very much.
Thank you, Eric. We have room for about 10 minutes of questions. Roughly.
So, Eric, can you elaborate on this whole address location problem? Because it seems like that's a simple thing.
Sorry?
It seems like it's simple to map addresses to locations, but you said that was a nightmare.
Yeah, I have a couple of slides, but you know what? We have already a lot of systems for that. Maritime industry, they have an address system. The airlines, they have an address system. Air navigation, they have another address system. If you go to Paris, you go to Charles de Gaulle, CDG. If you're a pilot, you're not going to CDG. You're going to Lima, Lima Fox, Papa, Golf. And with Lima Fox, Papa, Golf, you know everything you need to know. And so we have a lot of systems already, but there is no way we could attach them together to make it work. So you could have an address to fly to somewhere, but as soon as you touch the runway, you need to switch to another system. Then you're looking for a gate, and you're looking for a code for a gate. And then you need, when you pass the gate, you're on the road system. So maybe you look for a postal address, but postal address is not enough. And even postal address are not always accurate. So we are looking about some codes to combine things, maybe an IPv6 address for all locations or something like that. I don't know. But we are looking for some solutions to combine the different technologies and to have access to well-maintained addresses. For airlines, for the airline industry, for the pilot, it works well. It's very well maintained. They have everything they need. Otherwise, you can imagine when you are in the fog, you better rely on a good information system. But for when you touch the ground, it's a bit more messy. I did the experimentation for the IPIC conference in Paris. I ordered something. I think it was UPS. I'm sorry, but and they had problems because UPS, despite the name, is not a postal company. And here at MinParisTech, we are a small university, but we have a dedicated postal code. So it's and UPS is not able to read that code. So they send one parcel to they throw the parcels everywhere except to our place. Just an example.
Yes.
So recently I read the European Commission's white paper, and what it said was that apparently due to the negative externalities that we've seen recently regarding pollution, etc., the goal that they have right now is to reduce the road transportation by about 30% in 2020 and by about 50% in 2030. So just a question for that one, how far-fetched do you think this is? Because one of the countries with the most potential was France, actually.
Mm-hmm. Yeah, good. Yes, that's a really good point, because here I'm still based on cost function that are internal cost, or price signals that are based on internal cost. And if you look at negative impact or externalities, as it is today, there is a huge bias, because carbon for transportation, it's for free. You can release as much as you want. It's almost for free. There is no tax on the emissions. So The impact on your decision, 0. Congestion, huge in cities. I don't know here, but in European cities, we know that the negative impact of the external cost of a truck could be higher than the transportation cost itself. To give you an order of magnitude. Air pollution, also very important. So, what do? If we are not able to transfer that cost one way or another to the transportation system, it won't work. So maybe in major cities, I think major cities are good starting points. And in Paris, our mayor said in 2050, Paris should be carbon neutral. By no way we're gonna let vans enter city freely anymore and be carbon neutral. Even with electric vans, this won't solve the problem. It won't solve the congestion. It won't solve the environmental footprint of the batteries and the electric production and everything. So only the concentration, the efficiency could help. This won't solve everything as well, but it will help in the right manner. So I think that cities could be a good starting point. It's one of my next subjects to work with Paris, because so far their plan to make it work for freight in Paris, which is 1/4 of the emissions of Paris, is on one page. But when you read the page, you're looking for the other pages, and there is nothing more. So yes, it's a huge challenge.
Yes.
So, Dr. Eric, in the physical internet routing, you try to increase the efficiency and the utilization in the container transportation. But the companies who work with logistic companies previously, they have some biases and they like to have some constraints added for their own transportation and packaging. So will you bring in a limit to the number of constraints that a company can give? Because I feel that it might impact the efficiency that you're trying to bring in the physical internet routing.
What do you mean by constraints? I don't really get the point.
So what if they say that I have worked with UPS previously, so I'd like to allocate more than 50 to 75% of my packages to them. Whereas your program would suggest that I have this much space in UPS right now, and given that you want to reach this space at this time, maybe 25% of it will go in that, and the other 25% in some other transportation service.
Okay,
So
but okay, yes, you dedicate your business to maybe to UPS to up to 75%, but it doesn't mean that that doesn't mean that UPS needs to do everything on its own. Then UPS could maybe, if they are not so good in France, they could pass or hand over the cargo to another provider with a better network in France. That could be one solution, and you still have 75% of your business with UPS. But UPS will deal with the local provider. It's traffic exchange agreement. It already exists as bilateral traffic exchange agreement. What we are looking at is more plug-and-play traffic exchange agreement.
So, yeah, coming to that point again, are you saying that you'll allow the companies to give such constraints to you?
No, I have to say I have no power on companies. The only thing I can do is propose things to companies, and if they like it, then they implement part of it. But my power on companies, I have to say, very, very low.
Might have time for one last question.
So I would like to ask you about the bidding process and those dynamic routing of containers and also the carriers. So my point is that, do you have any idea on how dynamic this routing should be updated? Because, for example, when we have a shipment request, we need to assign a route to that shipment request. But maybe we cannot expect the carriers to update their routes like every second or every 1 minute.
Yeah, good point. Here, of course, to make the nice combinations, which is quite different from the freight marketplace that we have, which is really on the fly. We need some kind of time window to bundle things. And in the work, you can say, yeah, it's time window. It's a unit, one period. But of course, in real life, you need to adjust it according to the market constraints that you have. So we haven't studied that really in details, but I think that for CRC, it's going to be the day. But for other markets, I think it could be maybe hours, or maybe next hour when you need to enter a city, maybe an hour or less. But for B2B in Europe so far, a window of a day is, I think, it could work. We could start with that.
So you fix the carrier network or the relay network over the day, and then you update the containers?
I don't fix anything. I just gather all the services and all the offers, the requests, and we combine things. And here, as you saw, it could be done in a hub. It could be done also in an next hub. And we combine things. At each level, you combine things together. And when the process is finished, you start another one.
Okay, at this time, I think we will have to conclude. I'd like to thank Professor Bello for an excellent talk, and also thank you all for coming. It's always very appreciated. See you next time.
Thank you. Thank you very much.